Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 22. In this lecture, we'll discuss index of refraction. This topic is covered in Chapter 35, our textbook by Surway and Jowett. In previous lectures, we've discussed the wave speed for different types of waves. For example, we've discussed rope waves, and we learned that the wave speed for rope waves depends on the tension and the mass density of the rope. We've also discussed sound waves, and we know that for sound waves, the wave speed depends on the bulk modulus and the mass density of the medium through which the sound waves are propagating. In this lecture, we want to discuss the wave speed for electromagnetic waves. Electromagnetic waves are a little bit different because they can propagate through vacuum. Electromagnetic waves can travel through empty space. Of course, they can also travel through matter. Electromagnetic waves can travel through gases such as air. They can travel through liquids such as water. They can also travel through solids such as glass. When an electromagnetic wave is traveling through vacuum, its speed is precisely 299,792,458 meters per second, which in this class we will approximate simply as 3 times 10 to the 8th meters per second. This is the speed of all electromagnetic waves in vacuum, regardless of their wavelength or frequency. So radio waves, microwaves, visible light, X-rays, and gamma rays all travel with exactly the same speed when traveling through vacuum. This number happens to be a very special number in physics because it happens to be the ultimate speed limit of nature. As far as we know, nothing can travel faster than this speed. We don't exactly know why this particular number, but we do know that this particular number plays an important role as the speed limit of nature. Because it's such an important number, it gets its own designation. It's often denoted using the letter C. So henceforth, we'll use lowercase c to denote this very special number, which is the wave speed for electromagnetic waves in vacuum. This number is often referred to as the speed of light. However, remember that this number really is the speed of all electromagnetic waves, including light. So now we want to know what happens when electromagnetic waves pass through matter. What happens when these electromagnetic waves pass through a piece of glass or some volume of water or air, for example. It turns out for most materials, the atoms, the nuclei, and the electrons actually occupy a relatively small portion of the total volume of an object. Even inside a solid, the space between the atoms is essentially empty space. It's essentially vacuum. And within that empty space, the electromagnetic waves travel with this particular speed up here. However, from time to time, these electromagnetic waves will run into atoms or molecules. They will interact with the atoms. In fact, each atom can momentarily absorb the electromagnetic wave. It can absorb the energy and then re-emit it a short time later. The result is that as the electromagnetic wave propagates through, let's say, a piece of glass, it is repeatedly absorbed by the silicon dioxide molecules inside glass. Each one of these absorptions essentially delays the propagation by a very, very short fraction of a second. This effectively reduces the speed of the electromagnetic waves as it passes through the medium. For example, if we have a piece of glass and the width of this piece of glass is delta x, and we measure how many seconds it takes for light to travel through this piece of glass, and then we divide the distance by time, what we'll get is the speed of electromagnetic waves in glass, and we will find that that speed is less than the speed in vacuum, essentially because of the repeated absorption and emission by individual atoms and molecules. So as an electromagnetic wave propagates through a medium, be it a solid, a liquid, or a gas, it is repeatedly absorbed and re-emitted by the atoms or molecules of that medium. This process slows down the propagation of the wave. We can say that the average speed of the electromagnetic wave through that medium is reduced. The amount of propagation delay that is introduced depends on the atomic properties of the medium. It depends on the density of the medium, the number of molecules or atoms. It also depends on complicated factors like the affinity of the atoms of the medium for that particular type of electromagnetic wave. All of these complicated atomic interactions can be nicely summarized by a single number, which we call the index of refraction. The index of refraction, which is also known as the refractive index, essentially summarizes the amount of absorption and re-emission that takes place as a particular electromagnetic wave passes through a particular medium. In general, the higher the index of refraction, the more absorption takes place, and therefore the more delayed the electromagnetic wave becomes. Physicists have measured the index of refraction for different media. For diamond, the index of refraction is quite high, it's 2.42. For glass, the index of refraction is approximately 1.52. For air, the index of refraction is very close to 1, and for vacuum, where there is basically no absorption, the index of refraction is exactly 1. The index of refraction is denoted using the letter N. This might be a little bit confusing because in the past we've used the letter N to denote integers. In this context, the index of refraction does not have to be an integer. It's simply a number greater than or equal to 1. Given the index of refraction for a medium, we can calculate the wave speed in that medium. We can say that the wave speed in the medium, V, is equal to the wave speed in vacuum. This number here is 3 times 10 to the 8th, divided by the refractive index. Notice that the larger the refractive index is, the more absorption there will be, the more delays there will be, and therefore the smaller the average speed will be. Light travels through diamond relatively slowly. It travels through glass faster, it travels through water even faster, and of course it travels through vacuum at its fastest speed. Let's do a practice problem now involving the index of refraction. An electromagnetic wave propagating in vacuum with a frequency of 600 terahertz enters a piece of glass which is 0.5 meters thick. The index of refraction for that piece of glass is given to you as 1.52. How long does it take for the wave to travel through the glass? So this is a relatively straightforward problem. However, you need to recognize that the speed changes as the electromagnetic wave enters glass. What is the speed of electromagnetic waves in glass? Well, the wave speed is equal to the speed in vacuum divided by the index of refraction for glass. Recall that C, the speed of light or electromagnetic waves in vacuum, is 3 times 10 to the 8th meters per second. N is given to you as 1.52 in this particular problem, and we find that in glass, the average speed of electromagnetic waves is 1.973684 times 10 to the 8th meters per second. Notice I'm using a lot of decimal places here because I'm hoping to get a precise number. Now that we know how fast light travels, we can easily figure out the amount of time required to pass through this very thick piece of glass. The distance that the light has to travel is 0.5 meters, so we now take that distance and divide it by speed, and we find that the amount of time it takes to traverse the piece of glass is 2.53, repeating, nanoseconds. Here is part B of the same problem. Once again, we have an electromagnetic wave that is propagating in vacuum with a given frequency, and it's about to pass through a relatively thick piece of glass. Here we want to calculate the wavelength of the wave inside and outside of the glass. Notice that what we're given is the frequency of the electromagnetic waves, And we're also given n, the index of refraction, which allows us to figure out the speed. Once we have the frequency and the wave speed, we should be able to calculate the wavelength. Recall that these quantities are related as follows. The wave speed is equal to wavelength times the frequency. Now note that the wave speed inside and outside of the glass is going to be different. As the waves enter glass, they're going to slow down, and because the wave speed is different, the wavelength inside and outside of the glass is also going to be different. So what we need to do is calculate two different wavelengths, one inside the glass and another one outside of the glass. Before calculating the wavelength, let's talk about the frequency. The frequency turns out to be the same both inside and outside of the glass. The reason is that the electromagnetic fields outside the glass drives the atoms or molecules of the glass, and then those oscillating atoms in turn generate electromagnetic waves with the same frequency. We say that the source frequency determines the wave frequency. So the frequency doesn't change as the electromagnetic waves enter the glass. However, the wave speed does change. Outside the glass, we're going to assume we have vacuum, so we can say V out is equal to C, which is the speed of light in vacuum. And inside, we can say V is equal to C over N. Now that we have a handle on the frequency and the wave speed, we can talk about the wavelength. Wavelength outside the glass is equal to speed outside the glass divided by frequency outside the glass. Plugging in the numbers, we find that the wavelength outside the glass is 500 nanometers. However, as the waves enter the glass, they tend to slow down, and this slowing down also reduces their wavelengths. More specifically, the wavelength inside the glass is equal to wave speed inside the glass divided by frequency inside the glass. When we plug in those numbers, we find the wavelength there is approximately 328.9 nanometers. So the picture you should have in mind is something like this. Waves are traveling relatively fast with a relatively large wavelength. Recall that the wavelength of a wave is essentially the peak-to-peak distance. This is what we're calling lambda on the outside. And then as soon as this wave enters the glass, because its speed goes down, its wavelength also goes down. This distance here is what we're calling lambda inside the glass. And that is the end of this lecture. Thank you for your attention.